Okay, so during a crazy late night fight, Ronnie dances around the situation in their Italian apartment. Assume that the situation is the reference point. The graph below depicts Ronnie's movements for the first 33 seconds of the fight. So if you look at the bottom slide in your book, it says determine Ronnie's velocity for section B of the graph. First of all, if you're determining velocity and you have a position time graph, you automatically are thinking, beautiful. So jot down slope beside that, determine Ronnie's velocity, right? So just jot down slope. And let's go look at section B. Let's go look at section B. And some of you doing the slope calculation, some of you are counting lines. Like to me, I just count lines. That's what I do. How many over? How many down? 1, 2, 3, 4, 5, 6, 7. And then you just got to figure out how, yeah, each line is worth 1, so we're good there. Okay? So for that first one, Ronnie's velocity will be 7 over 4. Positive or negative? Negative, because you're losing 7 meters in 4 seconds. So for this position time graph, for section B, this person is moving left. And then 7 over 4 is what you'd want to calculate. And then you would always look at the units. You have meters on top and seconds on the bottom. Okay, let's go to the second bullet. And you can calculate that for yourself. 1.75, right? No quiz? Yeah, negative 1.75. Second bullet, what is Ronnie's displacement at 33 seconds? For a position time graph, if you're asking for displacement, you're just reading the graph. So for that second bullet, please just put read the graph. So go read the graph at 33 seconds. 30, 31, 32, 33. What value is that down there? Right here? Negative 7. So for that second bullet, negative 7 meters. That's the displacement. All right, good question. Is negative 7 meters equivalent to positive 7 meters left? Yes. So you can communicate either way, especially because there's like a legend over here that tells you that negative is left. So you could just leave it as negative 7 meters, or you can put positive 7 meters, comma, left. Both of those communicate the same thing. Third bullet. During which portions of the graph is Ronnie displaying uniform motion to the right? First of all, is this entire graph uniform motion? Yes. Why? Yeah. Linear. DT, linear, uniform. That's like a word association. If your DT graph is linear, it's uniform motion. Uniform motion, no acceleration. The speed stays the same. That was weird. So which portions are you traveling right? Careful. There's a difference between position and motion. So like in section B, your position is to the right of the reference point, but you're traveling left because you're going back towards the origin. So here, you're on the right side, but you're traveling left. Okay? So third bullet, it's A and C. Third bullet is A and C. Determine Ronnie's acceleration during the first 10 seconds of the fight. I wonder if that's for the next question. That would be 0, though, if you're using this graph. So the reality is, obviously, in real life, you'd have to accelerate. But these sharp points are sort of like mathematical tricks. These sharp points, they ignore the acceleration. So it's like, oh, you're traveling at a constant rate this way, and then magically you're traveling at a constant rate this way without any acceleration in between? Is that possible? That's not possible, is that? So this sharp point here is like a mathematical trick. Okay? So yeah, for that last bullet, the acceleration is 0, which we explained on the whiteboard there. Okay, VT graph for Snooki on the boardwalk. What show is she from? Jersey Shore? You know that show? Oh, it's these chachi guys with spiky hair and spray tans. Okay, so you're reading the bullets underneath the graph in your workbook. So, again, you're doing a test or something, you're doing a quiz. Just have a quick check at what the y-axis is. Thank you. This is VT, so we have to sort of switch how we think about it a little bit. This is the speed. You're modeling the speed. So, like, before we answer any questions, what's the speed for this interval? Are you moving? Stationary. What's happening to your speed on this interval? It's increasing at a constant rate, so you're accelerating. And your acceleration value is constant. You never have a changing acceleration in this class. Here your velocity is, careful, your velocity is, yeah, you're 8 meters per second for a certain amount of time. You're going to cover some distance, right? Definitely. You're traveling at 8 meters per second for a certain amount of time. You're covering distance. What's happening here? Slowing down, decelerating, both excellent vocabulary. Constant velocity, slowing down, constant velocity. Okay, let's answer these bullets. During what time intervals, if any, is Snooki accelerating north towards the beach bar? So accelerating north, let's put a scale on here for ourselves. Positive will be north and negative will be south. It doesn't look like we have any negative velocities. So she travels towards, oh yeah, we do have some. Let's just be careful. The positive and the north, the positive for north and the negative for south is for the velocity. So if you're above the x-axis, you're traveling north. If you're below the x-axis, you're traveling south. So acceleration, though. How do you find acceleration from a VT graph? Slope. So write that for the first bullet. Slope. So accelerating north, she would need to be speeding up or speeding down? Speeding up. So positive velocities. Where do you see positive velocities? Or pardon me, positive accelerations, positive slope? This section? Let's calculate the slope of that section. This one, right there, that value is 3. And this one, that value for x is 11. So the change The change in x is 8 seconds. What's the change in y? Go from 0 to 8. 8 take away 0 is 8. So it's 8 meters per second change in 8 seconds. 8 divided by 8 is 1. So your acceleration is 1 meter per second square north. North because the slope is positive. Calculate the displacement of Snooki between 11 and 16. All right, so we're a VT graph. We did the slope, and what did we get? Acceleration. Now they're asking me for displacement. So how can I get the displacement? If you've been doing your homework, you remember it's area. Good. What time interval? 11 to 16. Let's just sketch in some lines. And you guys go to the x-axis. 11 to 16. Shade that region. We need to find the area of that rectangle. What's the length of that rectangle? 11 to 16 is 5. And it's 8 up, right? 8 times 5, 40. And if it helps, you can put those units. Meters per second for y, second for x. 8 meters per second times 5 seconds. What happens to those seconds? Yeah, you're left with 40 meters. And she's displaced 40 meters north. Okay, you guys can do the third bullet. You have enough skills to do the third bullet. I'll wait. Okay, so you've calculated negative 3 meters per second squared. Now making sense of what that even means. Maria. You go over one increment. One increment is worth 2. So that's a change in x, which is 2. 1, 2, 3, 4, 5, 6 down. Each increment is worth 1. So delta y is negative 6. 6 divided by 2, 3. You okay with that? Okay. Now making sense of this value. Her velocity is positive because it's above the x-axis, but her velocities are decreasing. So if this cart is the origin, this is the positive side, okay? She's traveling this way, but slowing down. She was going 8. She was going 8. Now she's going 3. Because the acceleration is pointing that way, even though she's moving this way. If the velocity and the acceleration vectors are in opposite directions, you will slow down. If the velocity and the acceleration vectors are in the same direction, you will speed up. Last bullet. During what time intervals, if any, is the object speeding up in the positive direction? That's the first bullet? Okay, nothing fancy there. Speeding up in the positive direction. That's this bullet here. Yeah, I gotta fix that question. Okay, so that's it for the notes. I don't want to do any more notes today.